Can someone give me an example of such a field?
I don't know, is group theory itself an example?
So calculus.
Calculus, yes, very good. Group theory is not an example. Group theory was already there in a very sophisticated and advanced form. Physicists didn't even know about it, okay, until they realized that they only knew about SU2. Okay, they knew that, oh, you needed SU2 and the Lorentz group, and we will discuss their definitions. Lorentz groups for, quantum mechanics. And this is because of Wigner. Wigner did very important work relating how these two groups had, has relevance for the formulation of quantum mechanics. But beyond that, nobody knew group theory really in physics. And a lot of the group theory applications started in the 50s and 60s with strong hadronic physics, and SU3 became important, and it was Murray Gell-Mann, and he actually re-derived a lot of the group theory stuff, not knowing that mathematicians had already done it. Okay. So yeah, calculus is a good example of, because Newton, invented calculus so that he could describe mechanics and why the gravitational force inside a spherical shell of matter is 0 and stuff like that. But I'm not sure Leibniz was interested in physics. Okay, good.
Does Fourier series count?
Fourier series does count. That's a very good example. Yes.
Fourier tried to solve the heat equation. And
exactly. So yeah. So a lot of times that's a great point that Nian is raising, and that's a problem that was assigned as part of the assignment in my quantum mechanics course, is that Fourier was trying to solve the heat equation. Okay, Fourier was trying to solve the heat equation, and the heat equation is a linear equation. And because it's a linear equation, if you find a solution, two solutions, and if you add them and they have the right boundary condition, that's also a solution. So yeah, and if you're interested in how the heat equation gave birth to Fourier series, there's a wonderful video by 3 Blue 1 Brown that I would recommend that you watch on YouTube. Okay, any other examples?
The theory of distributions.
The theory of distributions, that's another great example. Dirac came up with this idea of a Dirac delta function, and which is not really a function, it's a distribution. And that gave birth to the theory of generalized functions. And that's a very useful tool in applied mathematics and theoretical physics. Okay, any other examples?
Sir, did the brachistochrone problem give rise to the calculus of variations field?
Right. So the brachistochrone problem is the problem where you have some sort of, can you remind me what
okay, yeah, that's basically the minimal time path that you basically go through 2 points under uniform gravity.
Yeah, exactly. So that gave birth to the calculus of variation. And of course, this is kind of a, physicists think of a problem, or mathematicians, and then say, oh, let's solve it. And a lot of times these solutions don't really give birth to anything new, but sometimes they give birth to new stuff, right? So yeah. Okay, so any other ideas?
Sir, I have heard that the invention of spinors in physics has some mathematical new investigation for mathematicians.
Oh, yeah, spinners, right?
Yes, sir.
Yes. So that's a very interesting comment. Spinners in physics were introduced, I think, first by Pauli, as in a non-relativistic setting. It was a non-relativistic, spin in, like spin in non-relativistic quantum mechanics, and later it was generalized to relativistic quantum mechanics by Dirac. But spinners are interesting because they're neither vectors, nor are they scalars or tensors, okay? And you cannot make a spinner out of a vector or a tensor in any possible way. However, the other way is possible. Spinners can give rise to vectors and tensors. And Dirac, formulated it is called the Dirac. So yeah, spinners had a huge impact on both physics and mathematics. It turned out that something related to spinners was already there in mathematics. People just didn't realize it. And that's what is known as the Clifford algebras. Okay. But with the advent of spinners, one got like, there's actually a new kind of geometry called spin geometry. And then also like spin groups. And so for example, if I give you some manifold and I tell you, can you find on this manifold a vector field that exists everywhere, right? So, so if it's a two sphere, so suppose this is a two sphere, and a vector field is essentially just a collection of arrows that change smoothly. The question that I'm asking is that, do you think there's an answer to that such a vector field exists where it's not zero anywhere on this manifold? Should I write down the question? Let me write down. Okay. Does there exist? This is not exactly spinner, but it's related to something I'm going to say about spinner. Does there exist a vector field? What is a vector field? A vector field is just a bunch of small arrows on a manifold at every point, which change smoothly. Does there exist a vector field that is non-zero everywhere on a two sphere? What do you think is the answer is?
I think I remembered this problem, but I don't exactly remember the solution. I think it's either 1 or 2 points have to be zero on the sphere.
I think like it's the Brouwer fixed point theorem. So
Exactly. Nahi is right.
Is it related to the hairy ball theorem?
It is, yeah, exactly. It is called the hairy ball theorem. Yeah. Or as a fixed point theorem by, is it Brouwer or, yeah, Brewer, right? Yeah. So, so the answer is no. such a vector field cannot exist. And that's kind of related to, so that's a topological question. So when we go to spinors, you can ask similar questions. If M is a manifold, does it admit a globally defined, say, spinor field? It's called the spin structure or something, mathematically. And the answer is, there are restrictions on the manifold when we cannot do this. And this has, so spinors give rise to new topological invariants. And, they give us a new way of thinking about geometry that weren't there before spinors. But in physics, spinors are used in physics. Spinors are used to describe fermions. That is spin half or integer multiple or odd integer multiple of spin half particles. Okay, so any other ideas?
So the whole field of partial differential equation has motivations in physics.
Yeah,
I mean,
in fact, group theory is actually an outgrowth of trying to come up with a formal way of solving PDEs, like coupled PDEs, right? So Lie groups and stuff like that are related to that. So, it's huge. So I'm very glad that you guys know all of this and you're thinking about it. So maybe we should now go and start our main topic. By the way, I think there's a Ajan is happening now. I hope you have time for the prayer. We shall end the class at 6:20. Do you think that's going to be a problem?
No, sir, there'll still be time.
Okay, awesome. Thank you very much. All right, so let's start with Y groups. Okay, so